We're going to talk about complement of an event, because sometimes it's easier, instead of finding the probability of an event directly, it's easier to find its complement, C-O-M-P-L-E-M-E-N-T, and then use that to find the probability you're looking for. Well, in order to understand the complement event, you have to understand this fact here, that the sum of all probabilities in the sample space is 1. Which means, for example, the probability of rolling a heads is half. Probability of rolling a tails is a half, right? So the probability in the sample space of all probabilities in the sample space of rolling a heads or a tails or flipping a coin is equal to 1. And this little fact is going to help us out, because sometimes it's easier if you're asked to find the probability of finding something, the probability of not rolling something. For example, right here you're asked to find the probability of not rolling a snake eyes. Instead of actually counting all of the rolls of not snake eyes, it's easier to find what's the probability of rolling a snake eyes and then do 1 minus that. 1 minus that probability. That is what the probability of a complement is. You could find the probability of not an event occurring by doing 1 minus the probability the event occurred. So instead of coming over here and saying which one of these are not snake eyes rolls, a 6 and a 6, a 6 and a 5, and saying, counting each of these, why not instead find the probability of not getting snake eyes? Why not instead do 1 minus the probability of rolling a snake eyes? It's really easy to find the probability of rolling a snake eyes, right? There's only one of them. So the probability of rolling a snake eyes is 1 over 36. And so the probability of not rolling a snake eyes would be the other 35 out of 36 rolls. Alright, we're also going to be talking about in this section finding probability with permutations and combinations. This is a pretty classic story problem here about using these 4-digit codes or passwords. Well, Rick was given a 4-digit code that doesn't have repeating numbers. What's the probability he would receive a code of consecutive numbers? So you want to know the probability of his password. And his password, remember, you always go back to the definition of theoretical probability, which is favorable outcomes over the sample space. The favorable outcomes here are these consecutive number passwords, right? And then the sample space would be any 4-digit password. Alright, so maybe it'd be easier to find the possible 4-digit passwords in the sample space first. Remember, because they don't repeat, the first number in the password would have 4-number password would have 10 options, right? 0 to 9 would be 10 digits. Then the next one, because it doesn't repeat, would be 9, and then the next one 8 and 7. Multiply them together. That's going to be your sample space denominator of 5,040. Now, another way you could come up with 5,040 is by using permutations. Remember, order does matter. Order does matter in the story problem, because the password 3459 is different from 3495, even though they're made up of the same 4 numbers. So we would be, with 10 numbers, we would be P4, 10P4. This number also would give us 5,040, so you could use permutations to find the sample space denominator. Now the numerator would be to actually find the consecutive, 4-digit consecutive numbers. I mean, we could start, remember, 0 is a number, with 0, 1, 2, 3, 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 6, and eventually you're going to run out of space because you're going to hit 9. So this is not going to go on infinitely. It stops with 6, 7, 8, 9. What you have here are 7 consecutive passwords, but you also could go the other way, 3, 2, 1, 0, right? You could go this way in terms of the password. So if we repeated that and wrote these all backwards, you would realize that there are 14 passwords total. Thus our probability would be 14 over 5040, which reduces to 1 over 360. Okay, lastly, we're going to do something called geometric probability, and in this case, we're still using the concept of theoretical probability, that definition, which is favorable over total outcomes, or the sample space. But now the sample space is not a list of numbers or a counting of numbers. Our sample space is actually an area. It's a region. So what's the probability a point chosen at random in the figure is inside the shaded region? Well, think of it as like you're throwing dartboards, okay? And here is the dartboard target that you're shooting at, and you will get a bullseye if you hit something inside the shaded region. And so to find the probability of being in the shaded region, what you would have to do is you would have to find the area of the shaded region. That's what's favorable. And then you'd have to divide that by the total target, which is a huge semicircle, with these two little semicircles subtracted out of it. Okay, it'd probably be easiest for us to find the area of the semicircle first. If you know the area of a circle is pi r squared, so cut it in half would be a semicircle, and in this case, the radius would be equal to 3 because the diameter is 6 going all the way across. So that would be equal to pi times 3 squared over 2, which is 9 pi over 2. That is going to be your denominator. That's your sample space. Okay, in order to get the shaded region above, over here, we'd have to find the area of this semicircle, which we already know is 9 pi over 2. And then you would have to subtract off these little semicircles, right? And then that would be the area of the total region. So these little semicircles have a radius of 2 and of 1. And so if I did pi r squared with 2, that would be 4 pi over 2. That would be the bigger semicircle. And then if I did pi r squared, r now being 1, it would be pi times 1 over 2. Pi r squared over 2, because they're semicircles. So this would be equal to 5 pi over 2. Right? 9 minus 4 minus 1. Oh no, that's 4 pi over 2, sorry. 4 pi over 2. Because 9 minus 4 minus 1 is 4. So this would be 4 pi over 2. And I'm not going to reduce it because I'm dividing fractions. And the way you divide fractions is you multiply by this thing's reciprocal, the denominator. So that would be a 2 over 9 pi. And you're going to see that the 2's cancel out, the pi's cancel out, and you're left with a probability of 4/9. Now the last thing the book talks about, that's a 9, forgive me. The last thing the book talks about is something called experimental probability. And experimental probability is the exact same thing as theoretical probability, except for you're not actually considering in your brain like what's the probability of flipping a heads if you tossed a coin, but you're actually looking at a chart. You're looking at information, at data that you collected, and you're basing the probability off of that. So the probability of flipping a heads is 1/2, right? But let's say you actually flipped 4 heads, or 4 coins, and you got a tails, a heads, and a tails. So in this experiment, the probability of flipping a heads is actually 1/4. You see, regardless of what in theory you should have got a half, with the data from this experiment, you actually got 1/4. That's the difference with experimental probability, is you actually look at the chart that's given to you to come up with what the probability would be using that experimental knowledge data.